Today we're going to be covering a number of pre-calculus topics, and so we're going to start here with inverse functions.
A function is invertible if no 2 points have the same y coordinate. Now, we said that a function, no 2 points have the same x coordinate. Well, now we're saying that no 2 points have the same y coordinate, so none of the y's can repeat. In other words, every y corresponds to at most one x coordinate. This time we're going to have the horizontal line test, okay, because none of the y's can repeat, so horizontal line can't cross through the graph at more than once. To find the inverse, we're going to switch the x coordinate and the y coordinate, and then we're going to solve for y. So the idea here is that in inverses, the roles of the x and y switch. And please keep in mind, you may be looking at a graph and it passes that horizontal line test. It doesn't have any y's repeating. But it may be algebraically impossible to actually find the equation of that inverse. You may be looking at a graph and you know it's invertible, but you may not be able to get an equation for that, and that's okay. But let's say that I gave you this function and I said find f inverse. By the way, the -1 there, this does not refer to a negative power. This is the inverse function. Certainly I'm never going to say, hey, find f inverse, and it's impossible. Well, that would just be mean. I wouldn't do that. So if I asked you to find f inverse, find the equation of f inverse, then it's possible. So to find the inverse, we're going to switch the roles of x and y. So it becomes x equals 1 over 2y minus 5. And then go through and solve for y. So maybe reciprocal of both sides. 1 over x equals 2y minus 5. Add the 5 to the other side. Divide by 2. And this is my inverse. So my inverse is 1 over 2x plus 5 over 2. And yeah, I mean, you could write that in different forms. You could make that into one big fraction. Have a great time, but it's not necessary. This is a good answer. You found the inverse. That's all I'm looking for. When it comes to sketching a graph of f inverse, we can sketch that graph by considering the line y equals x. Here's the line y equals x. And this purple graph is supposed to be f, and I'm going to graph f inverse. Now, a couple things to consider. Let's consider this point on f. This is the point 2, 3. Well, inverse means that the roles of x and y switch. So if f has the point 2, 3, then the point 3, 2 is going to be on f inverse. Likewise, down here, -2, -3 becomes -3, -2. What about this point right here? And this point, and this point? Well, again, that dotted line is the line y equals x. These are all the points on f where the x and y coordinates are the same, which means that when you switch them for the inverse, you're still going to be the same place. So these 3 points are going to be where the f and f inverse graphs intersect. And this dotted line is going to act like a mirror. And so the f inverse graph is going to be the mirror image of f. We've got a few points to guide our function. There we go. So this would be a graph of f inverse. To graph f inverse, it's going to be the mirror image of f, where the mirror is the line y equals x. Now, first of all, talking about domain and range, or not first of all, but next of all, talking about domain and range, remember the roles of x and y switch. So the domain of f becomes the range of f inverse. The range of f becomes the domain of f inverse, because the x's and y's all switch. Now, the rest of this section is going to be interpreting the inverse, explaining the inverse. What does the inverse mean? And to understand that, again, it's the idea that the function and the variable swap. Let's consider this situation. Distance as a function of time. D equals f of t. Well, if you think of a function like a machine where you're putting something in this case, I'm putting in a value of t, and the function is telling me a value of d. In other words, I could say, okay, I've been traveling for 20 minutes. And this function will result in how far I went during that time. So I pick a value of t, 20, I plug it into my machine, and what I get back is that distance that I traveled in that time. The inverse switches those. So now the roles of input and output swap. So now the inverse, time, is a function of distance. Now we're putting the distance into this inverse, and we're getting back the time. So instead of saying, oh, I've been going for 20 minutes, how far did I go? That's the function. Now I'm asking the question, oh, well, I've traveled 15 miles. How long did it take me to do that? Now I'm picking a value of d, the distance that I traveled, putting that into my machine. And the inverse function gives me back a result that's time, how long it took me to do that. So let's consider this example. Let C equal F of Q be the cost in dollars for Dunder Mifflin to produce Q boxes of paper. And using correct units, let's explain the meaning of F inverse of 25 equals 1,000. Well, let's start with this. C equals F of Q. And by the way, the units are going to be a really good guide for this. So C is the cost. So the units for that cost is going to be measured in dollars. Q, well, we're told that Q is the number of boxes of paper. So the units for this would be boxes. Well, when I switch them, when I write the inverse, the roles switch. This time it's going to be Q equals F inverse of C. The roles reverse. C is still measured in dollars. Q is still measured in boxes, but now the roles reverse. So now, looking at the equation that I'm trying to explain, notice that this 25 is what I'm plugging into the F inverse function. Well, what am I plugging into F inverse? It's C, it's dollars. So this 25 would represent $25. And what do I get back? What is the inverse function equal to? It's equal to Q. It's equal to number of boxes. So this 1,000 would represent the number of boxes. So we have to interpret this. We have to write out a sentence telling me what does this mean. There are a lot of different ways to do that, but the one thing that I want to emphasize is that this 25 gives us a reference point, and I want your explanation to use that. The reference point meaning when we plug in this number, here's the result. So how about we say, when we spend $25. So I'm starting off by saying, when are we talking about? At what point in this process are we talking about? It's the point where we spend $25. When we spend $25, we will produce 1,000 boxes. There are a lot of ways to adjust this, and there are different ways to rephrase it. Certainly this is not the only answer. But the best thing about this is, number one, it says the units, $25, 1,000 boxes, and that 25 represents that input. So I would say a bad answer would be to write these in reverse. When we produce 1,000 boxes, we're going to spend $25. That would be a bad answer because, again, let me say that again. When we produce 1,000 boxes, it costs us $25. That sounds to me like I'm putting in the 1,000 and I'm getting back 25. That's not the inverse. That's the original function. That's F. When I put in the number of boxes and I get back the cost. When I produce 1,000 boxes, it's going to cost me $25. That, I think, is backwards. So I think that would be a bad answer. You want to make it sound like you're putting in 25 and you're getting back 1,000. Let's try this one. Suppose that D equals F of A is the cost in dollars for Apu to build a Kwik-E-Mart with area A square feet. Using correct units, explain the meaning of, okay, so F of 10,000. So again, we have here that F of A is equal to D, And let's remember what these represent. A represents square feet, the area of the store. And D represents the cost. So D would be, again, in dollars. And then if we switch it, F inverse of D is equal to A. So now it's F inverse of dollars equals square feet. Okay? So something to consider as we're going through this. So this 10,000, we have to decide, is this $10,000? Is this 10,000 square feet? Notice that it's a number that's plugged into the original function. Well, the original function, we're plugging in A. We're plugging in square feet. And the result, the function itself is equal to D. The function itself is equal to dollars. So F of 10,000 would be a dollar amount. F of 10,000 would be the cost in dollars. Notice I'm mentioning my units to build 10,000 square feet. And I mean, you can be more wordy than that. It's how much it will cost in dollars to build a Kwik-E-Mart that has an area of 10,000 square feet. Fine, whatever. You can be wordy about that. That's okay. But this gets across the idea. And then F inverse of 20,000. Again, now we're talking about F inverse. So now this 20,000 is a number being plugged into F inverse. Well, D is what we plug into F inverse. So this 20,000 would represent a dollar amount. And the result of plugging in that 20,000, well, F inverse, when we plug in a number, the result is square feet. So this time we're spending $20,000 and we're trying to figure out the square footage. So maybe this time it's the area. How about, instead of area, let's say size. This is the size in square feet that can be built for $20,000. But again, those units really drive everything. Before you think about those numbers, before you think about these functions, think about what the units are going to be for your answers, for these numbers, and that'll help you to really solidify what's happening. So don't just jump right into the explanation. Think about the units. It will help a whole lot. First of all, introduce what it means to be a logarithm. If we talk about the log base a of x equals y, okay, so here's the base here of a. This would be equivalent to making the statement that using exponents, that a to the y is equal to x. And the way that I always visualize this is I always picture this a over here zooming over and becoming the base of an exponent. So it becomes a to the y on one side. And then when the a is gone, the log is gone. So you just have the x on the other side. So a to the y equals x. Okay, so that's what it means to be a logarithm. And more, just make sure we're on the same page. We could also talk about the natural log. And the natural log just means that we're going to use base e. This should not be new for anybody, but certainly worth mentioning. Some properties, some laws of logarithms. First of all, the natural log, where there's the product inside of the log, is equal to adding two logs together. So the natural log of a times b equals the natural log of the first plus the natural log of the second. By the way, I should mention that these properties I'm writing out using the natural log, but of course they're true for any base. If there's division inside of the logarithm, that's the same as subtracting logs, so the log of the top minus the log of the bottom. And then if you've got the natural log of a to the n, that power on the inside, we can bring it out in front. I do want to emphasize that if you've got the natural log of a times the natural log of b, there is nothing you can do to simplify that. Okay, it's only when you're adding two logarithms together that you can combine their insides. Likewise, if you are, if instead of like this, you've got the natural log of a over the natural log of b, that is not the same thing as we've got over here. Here, it's the natural log of 1 quotient. Here I've got a log divided by another log. This right here, there's nothing you can do to simplify this. Also, you can only simplify if you're multiplying inside or dividing inside. So for example, if I've got the natural log of x plus 5, there's nothing I can do to split that up. There's no property of logarithms that says what to do if you're adding inside of a log. So there are some, we've got these properties of logarithms, but there are certainly some ways that they cannot be used. There are certain limitations to those. Okay, so first, just to play around with these properties, let's consider this example. Oh, I'm sorry, we have three more properties. The log base a of a to the x is equal to x. Different ways to think about this, but basically the exponent and the logarithm are inverse operations. The log cancels the exponent, and we're left with just this power x. If we switch the order, same thing. E to the log base e of x is equal to x. The log and the exponent cancel. And the other thing to keep in mind is that the natural log of 1 is 0. Okay, and again, that's true for any base. Any log, when you plug in 1, you're going to get back 0. So now let's play around with these. Let's express this as a single logarithm. In other words, we're going to bring all this together until our final answer is going to be the log of something. Well, different ways to go about this, but I think the best thing is to bring the 2 inside. So we have the log of x squared. Bring the 3 inside, so we have the log of y cubed minus the log of z. And now we learned that if we are subtracting 2 logarithms, we can combine those by dividing the insides. So we're going to have an x squared divided by y cubed, and we're also subtracting the log of z, so I'm also going to divide by z. So there's my answer. So just a real basic example. Again, you guys have seen these before, but just to remember what it is that you could be asked to do. Now, the main use of logarithms, as far as I'm concerned, the main use is solving exponential equations. So something like this: solve 20 times 2 to the x equals 50 times 1.04 to the x. So again, different ways to go about this. I think that the easiest way to do this problem would be to make it so that there's only one exponential thing. In other words, I'm going to divide both sides by 2 to the x. I'm going to turn this into one big exponent, but then I also want to move the 50 to the other side. And so I get, if I reduce this fraction, I get 2/5 equals 1.04 divided by 2 to the x power. Okay, basically get the exponent by itself. And then to get rid of this exponential, we're going to do the inverse, which would be the logarithm. I'm going to take the natural log of 2 over 5. On the other side, the natural log of 1.04 over 2 to the x. I mentioned this previously, but I'm using the logarithm here. I'm using the natural log. You can use any base you want. I'm going to encourage you to use either the natural log or the common log, base 10, just because those are the buttons we have on the calculator, but you could use any log you want. The advantage is now, when there's a power inside of a logarithm, that power x can be brought out in front. So I can write this as x times the natural log of 1.04 over 2. And then if I want to find x, well, this natural log of 1.04 over 2, it's ugly, but you know what? That's just a number. To get the x by itself, I'm going to divide that number to the other side. Natural log of 2/5 divided by the natural log of 1.04 over 2. And then from here, I can pick up my calculator, get an answer. So we've got the natural log of 2/5. Don't forget to close parentheses, divided by the natural log of 1.04 divided by 2. And I end up getting 1.401. Don't forget, 3 decimal places. Always 3 decimal places on your answer if the decimals go further than that. Okay, so using logarithms to solve an equation. Let's try another one. Let's try 10e to the x equals 7 to the x. Now, we could start this problem the same way we did the last one. We could move the e to the x to the other side. But rather than doing that, why don't we just take the natural log now? Natural log of 10e to the x equals the natural log of 7 to the x. Let's just take the natural log now. On the right side, no problem. We can bring that x out in front. So this is x times the natural log of 7. On the right side, there are a couple things that we would like to do but can't. First of all, I'd like to be able to say, hey, the natural log and the e cancel each other out. So we get, well, they don't cancel each other out because there's a 10 sitting here. Likewise, I see an x as a power inside. Well, this power, I can't just bring this x out in front like it did on the right side, because here, this entire inside is not to the x power. E is to the x power, but 10 is not. In other words, I can't do either of those two things that I would like to do until I fix it. And here's how I'm going to fix it. I'm going to think of this inside stuff as 10 times e to the x power. And if I'm multiplying two things inside of a logarithm, that means that it's the log of the first plus the log of the second. We have to do this. We have to split it up into these two pieces. And now I could bring the x out in front. Now I'm left with a natural log of e's, which is just 1. And now I've got a problem that I can solve. To get x by itself, I'm going to move the x to the other side. So the natural log of 10 equals x ln of 7 plus x. I can factor the x out of the right side. So natural log of 7 plus 1. And then divide. X equals the natural log of 10 over the natural log of 7 plus 1. And I could get a decimal, but notice this is a fairly painless answer, so I could definitely see a problem like this showing up on the non-calculus part of the test. Non-calculator, excuse me. It's all calculus on the test, but I could see it showing up on the non-calculator part of the test. All right, word problem. The half-life of a substance is 12 days if there are 10.32 grams initially. Write an equation that represents the amount A of the substance after t days. When will there be 1 gram left? Okay, well, let's start off by realizing this is an exponential model. And you'll remember from the first day there were 3 different ways we could write exponential models. I'm going to write P equals P naught e to the kt power. You could also do a to the t power. That was another option, a to the t. That would work just fine here. I would discourage the 1 plus r to the t power. That's useful mostly if you're given an annual percent or something like that, but in this case we're not. But you know, you have plenty of choices. We know that our initial amount is 10.32, so let me put that in there. And we know that the half-life is 12 days, which means that when t is equal to 12, the amount of the substance left is half of what we started with, 5.16. Now, let me take a step back and just say that I'm using one of these 3 exponential models. Some of you may have learned an exponential a model for half-life. You are very welcome to use that. I don't usually teach it because it's just one more thing to memorize that isn't necessary. But you are very welcome to use a half-life formula if you know it. All right, so to solve for k here, I'm going to divide. If I divide, I'm going to get 1/2 equals e to the 12k. Natural log of both sides. When I take the natural log, it's going to cancel with the e, so I'm left with 12k. So k is equal to natural log of 1/2 divided by 12. And let me get a decimal for that one. So k is equal to negative 0.058. And I'm going to store this value. Remember, we want to store any values that we might use later on, and we certainly will use this one. So I'm going to store that as the letter K. All right, so let me set that aside for a second. Let's cover up Homer. All right, now I found K, and that's great. The problem is very specific. It says, write an equation that represents the amount A. Oh, I used P. I'm sorry. I should have used the letter A, but you get the point. All right, fine. Let's change that. A, and A. By the way, on a test, I really don't care if you use the letter P instead, but may as well be consistent. All right, but my point is the problem says write an equation for A. You need to write A equals 10.32 e to the negative 0.058t. I need to see that step. No matter what else you're asked to do, this problem asks you for two answers. One of your answers is that equation, and I need to see it. The other answer is, okay, how much time has to pass before there's 1 gram left, and we'll get to that. Now, one other thing I want to point out is that it makes sense that we got a negative answer for K, because this is an exponential decay model, because the substance is decaying, which means that we would expect a negative power for that E. Now, the last step here, we want to know when is there 1 gram left, so the amount is 1. And we want to know what is T. Well, let's go through and solve. Divide. 1 over 10.32 equals e to the negative 0.058t. Natural log of both sides. Let's go here. Natural log of 1 over 10.32. Once again, the natural log and the e cancels, so equals negative 0.058t. Divide. So on my calculator, I am doing the natural log of 1 divided by 10.32. So there's my natural log. Remember, we're going to divide by this number, but don't retype that decimal. I'm going to divide by K. That's what I called my, my decimal. So if I hit enter, 40.408. And I think here we're talking about days. Okay, so we got our answer. Again, just a reminder, calculator use. Don't forget to store decimals in the middle of a problem. Don't forget to write your final answer in 3 decimal places at the end of the problem. Okay, so previously we talked about, I think it was last class we talked about, as x goes to infinity, which functions dominate which other functions? Well, logarithmic functions are always dominated by increasing power functions. So as x gets really, really, really big, if even though the logarithm is going to infinity, right, remember that a logarithm looks like this. Even if a logarithm is going to infinity, it's not going to infinity as fast as an exponent, or even a power function, or even the square root. The square root is an example of a power function. Now, I don't know how they start out at the beginning, but eventually that power function will end up on top. So even the square root is going to go to infinity faster than the logarithm. Now, we've got a bunch of functions we've talked about, and oh, this dominates that, but this dominates that. There's a hierarchy going on. The question is, well, what's the upshot? What's the overall summary of that, of those functions? And to remember that, we're going to use n to the n febble. No, I did not make this up, but sure sounds like I did. Actually, I got this from a math conference I went to. One of the other teachers was sharing this. And n to the n febble means these are the functions and the hierarchy in which they go to infinity the fastest. So we have n to the n, factorial, exponent, polynomial or power could also go in that for polynomial, linear, and then at the bottom here is logarithms. And what this hierarchy means is that as x goes to infinity, the functions on top grow fastest, the functions on the bottom grow most slowly. They all go to infinity, but some go faster than others. So to help you remember the order, end of the invertible. All right, so an example here. Consider this function g of x equals 2 over e to the x plus 5. First question, is g increasing or decreasing? Well, we know that e to the x is always increasing. Okay, e to the x looks like this, always going up. So e to the x is always increasing. So add 5, still always increasing. Well, if you've got 2 divided by a number that's getting bigger and bigger and bigger, 2 over 100, 2 over 1,000, 2 over a million, 2 over a trillion, as the bottom gets bigger and bigger, the whole thing is going to become smaller and smaller. So g of x is a decreasing function. And notice that because e to the x is always increasing, no matter what x I choose, g of x is always decreasing. Now the second part of this question is this. Explain why g must be invertible, and then find the inverse function. Now, to explain why g is invertible, that doesn't mean, oh, find g inverse and, oh, it's invertible because I got an answer. That's not good enough. Invertible means that none of the y coordinates repeat. Well, what we just learned in part A is that g is always decreasing. G is always going down. Maybe sometimes it's not so steep, and maybe sometimes it's really steep and whatever. I don't know what the graph looks like, but it's always going downward. It's always going in one direction. And for that reason, this function has to be invertible. The y's can't repeat, because the only ways y's can repeat is if the graph goes down but then comes back up again. Then you get the y's that are repeating. But if the graph is always going in one direction, by the way, the word we use for that is monotonic. Monotonic means always going in one direction, either always decreasing or always increasing. Because the graph is always going in one direction, the function has to be invertible. So that would be the first part of our answer. Y is invertible because the graph is monotonic, because the function is monotonic. But now to find g inverse, let's remember we switched the x's and y's. So x equals 2 over e to the y plus 5. And we solve for y. Let's see, we could reciprocate both sides. So 1 over x equals e to the y plus 5 over 2. Multiply the 2 to the other side. Subtract the 5 to the other side. And then finally, oops, that should be e to the y. And then finally, to get the y by itself, we can take the natural log of both sides. So the natural log of 2 over x minus 5 equals e to the y, or excuse me, equals just y, because the natural log and the e cancel each other out. So g inverse equals the natural log of 2 over x minus 5. And there we have it. All right, well, that is the end of the lesson. I'm going to ask you guys to please get started working on the homework. Thank you.